student just sent me this one, so let's play with this. I'm not even sure how the proof is going to go, but this will show you the value of the discussion, because the discussion won't be the proof, but this is how any mathematician approaches a claim. So, we wish to show that AB plus CD squared is less than or equal to quantity A squared plus C squared times B squared plus D squared. Okay, in my discussion, on the left-hand side, I'm going to distribute to figure out what that left-hand side actually is. And it's A squared B squared plus 2ABCD plus C squared D squared. On the other hand, on the right-hand side, this would also be a distributive property here, and first times first, A squared B squared, then we have an A squared D squared, then we have a B squared C squared, and then we have an C squared D squared. C squared D squared. Okay, so as I'm looking at this, I can see that these are on both sides. Remember, we're hoping that this will happen. Those are on both sides. Oh, forgot my plus sign. Plus sign, plus sign. C squared D squared is on both sides. Oh. So if I subtract 2ADBC, I'm reordering this just so that I can see it more clearly over here. I'll have minus 2ADBC, and that'll leave me with a 0 on the left-hand side, which I'll be hoping is less than or equal to A squared D squared minus 2ADBC plus B squared C squared. Can you see why I'm pretty excited about that? Over here we have AD minus BC quantity squared. This is a perfect square trinomial type piece with the first one squared, the second one squared. It's a minus sign this time, but the same little prefix is in the middle. And of course, anything squared, any real number squared, will always be bigger than or equal to 0. So now we have success here. I can see that I have a perfect square, and a perfect square is always non-negative. So this actually leads me into the proof now. I know exactly what I'm going to do for my proof. So ready to take a shot at it on your own? Pause the video, think about what this says, and try to perform the proof on your own. Now, assuming you gave it a shot, let's do it together. So we're going to come down to that last statement. So since A, B, C, and D are positive, or sorry, they're not positive, since they are reals, we know for a fact that, what was it again? It was an AD minus BC squared will simply always be larger than or equal to 0. So, what does that mean? Expansion would mean that A squared D squared minus 2ADBC plus B squared C squared would certainly be bigger than or equal to 0. And that's just by expanding, right? By multiplying out those two binomials. Then, adding, what do we have to add to both sides? We're going to add 2ABCD, because remember we had to move it over from one side, and we're also going to throw in those other quantities that we wanted, A squared B squared and C squared D squared, to both sides of the inequality, will yield, let's see, on the left-hand side, we'll now have an A squared D squared, we'll have the B squared C squared, we'll have these two new ones that we threw in, A squared B squared, and we'll also have a C squared and a D squared. So I'm putting all of those on the left-hand side. And on the right-hand side, we'll just have those three pieces. So I'll write them as A squared B squared plus 2ABCD, writing them in a different order, plus c squared d squared. Then factoring yields, so on the left we can factor by grouping, and I can see here that we have a d squared that's common, so I'll put a d squared here with a squared plus c squared plus, here's b squared, so I'll put a b squared that's common with a squared plus c squared, and that'll be bigger than or equal to ab plus cd quantity squared, and thus factor out the d squared plus b squared because the a squared plus c squared is common. We'll get a squared plus c squared multiplied by d squared plus b squared, so b squared plus d squared, bigger than or equal to ab plus cd quantity squared as needed.